Let's discuss about the purification of colloidal solutions. The colloidal solutions, when they are prepared, they contain large amount of electrolyte and some soluble impurities. Now, small amount of electrolyte is very much required for the stability of the colloidal solution, but if large quantities are present, then this leads to the coagulation of the colloidal solution. Coagulation means that the colloidal particles start settling down and they lose their colloidal dimension. So it becomes very important to reduce the amount of these impurities to a requisite minimum, and this is known as purification of colloidal solution. The various methods for purifying the colloidal solutions are dialysis, electrodialysis, and ultrafiltration. In the dialysis method, the dissolved substances are removed using a suitable membrane. The membrane can be a cellophane sheet or an animal membrane or a parchment paper. The apparatus used for this purification method is a dialyzer. So let's see this dialyzer. This dialyzer contains a bag of suitable membrane. This is a bag of suitable membrane and it contains the colloidal solution, and it is suspended in a vessel in which the fresh water is continuously flowing. So from this membrane, the ions and other molecules, they diffuse into the outer water, and the pure colloidal solution is free from all these impurities. Then we come to the electrodialysis method. This dialysis is a very slow process. If we want to increase the speed of the process, then we can apply an electric field, but we can do so only if the impurity is that of an electrolyte. If the impurity is that of an electrolyte only, then what we do is that we fit the electrodes in this dialyzer. So what happens when on fitting the electrodes, the cathode and anode here, then what happens? The ions, they start moving towards the oppositely charged electrode. As a result, the colloidal solution is again purified. It becomes free from all the impurities as the impurities start moving towards the oppositely charged electrodes. So the next method is an ultrafiltration method. In ultrafiltration method, we use a ultrafilter paper. Now how we prepare this paper? We prepare this paper from an ordinary filter paper. This ordinary filter paper is dipped in a colloidal solution. Now what is this colloidal solution? It is a 4% solution of nitrocellulose in a mixture of alcohol and ether. So we dip this ordinary filter paper into this colloidal solution, and then what we do is we harden this by putting it in formaldehyde, and then finally it is dried. So the ultrafilter paper becomes ready. This ultrafilter paper can be used to separate the colloidal particles from rest of the materials. The colloidal particles are left on the ultrafilter paper, and then they can be again stirred with fresh dispersion medium to get a pure colloidal solution. This ultrafiltration is also a very slow process. If we want to increase the speed of the process, then we can apply suction. Thus, ultrafiltration. In the ultrafiltration process, we have separated the colloidal particles from the soluble impurities. Let's discuss about the properties of colloidal solution. First is the colligative property. The colligative properties depend upon number. If we compare the colloidal solution and true solution, we find that the colligative properties are more for true solution as compared to colloidal solution, because the colloidal particles, they form bigger aggregates, and so the number of particles in a colloidal solution is comparatively small as compared to a true solution. So if we have colloidal solution and true solution at same concentration, the colligative property will be more for true solution. Now we come to the Tyndall effect. The Tyndall effect is the scattering of light by the colloidal particles, and as a result of this scattering, the path of the beam is illuminated and we are able to see a bright cone which we called as Tyndall cone. This effect is observed if we view the colloidal solution in a direction at right angle to the passage of light. Then we find that the path of the beam is illuminated by a bluish light. This effect was observed by Faraday and later on studied in detail by Tyndall, and that is why it is called Tyndall effect. The Tyndall effect can be observed during the projection of pictures in the cinema hall due to the scattering of light by the colloidal particles. The Tyndall effect is observed if two important conditions are satisfied. This is important. The first condition is that diameter of the dispersed phase should not be much smaller than the wavelength of the light used. That is, they two must be comparable. And secondly, the refractive index of the dispersed phase and the dispersion medium should differ greatly in magnitude. Now we come to the next is the color. The color of the colloidal solution depends upon wavelength. The wavelength depends upon size and nature of the particles. The color also depends upon how we view the colloidal solution. For example, if we have a mixture of milk and water, it will appear blue when we view it with reflected light, and it will appear red when we view it by the transmitted light. The finest gold soul is red in color, but as the particle size increases, it appears purple, then blue, and finally golden. Now we come to the next Brownian movement. It is the zigzag motion of the particles. So this zigzag motion of the particle is because of the unbalanced bombardment of particles by the molecules of the dispersion medium. That is, the molecules of the dispersion medium keep on hitting these colloidal particles, and as a result they have zigzag motion. This zigzag motion is very important because it do not allow the particles to settle down, and hence it is responsible for the stability of the soul. So this was discovered by a British botanist, Robert Brown, and that is why it has been given the name Brownian movement. Let's discuss the next property of colloidal solution, that is charge on colloidal particle. This is a very important topic, and this year question appeared in the board from this topic. The colloidal particles, they always carry charge. The charge can be positive or it can be negative. We can see the different examples of positively charged souls and negatively charged souls. Hemoglobin is a positively charged soul. Clay and charcoal are negatively charged soul. Copper, silver, gold are negatively charged souls. The arsenic sulfide, which you prepared by double decomposition, is a negatively charged soul. Then the methylene blue is a positively charged soul. Hydrated metallic oxides, positively charged soul. So please go through this table. The question can come from this table. Now if we have equal and similar charges, then what will happen? The equal and similar charges, if they are present on the colloidal particles, they will repel each other. And as a result of this repulsion, what happens? They will not form aggregates, and this is responsible for providing stability to the colloidal souls. That is, when aggregates are not formed, the soul will not lose its colloidal dimensions, and thus it will be stable. So equal and similar charges on colloidal particles are responsible for providing stability, because the repulsive forces between the charged particles prevent them from aggregating when they come closer to one another. Various theories are there which explain that why charge is present on the colloidal particle. The first theory is that whenever there is dispersion of metals using electric field, there is electron capture by the soul particles. This is one theory. The second theory is preferential adsorption of ions from the solution. This is the second theory. And the third theory is formulation of electrical double layer. The most accepted theory is the preferential adsorption of common ions from the dispersion medium. The soul acquires positive charge or negative charge by preferential adsorption of positive or negative ions from the dispersion medium. This When two or more ions are present in the dispersion medium, the preferential adsorption of the ion common to the colloidal particles usually take place. Let's understand this. For example, we have a silver nitrate solution and we add it to a potassium iodide solution. So silver iodide will be formed. As potassium iodide is the dispersion medium, so silver iodide will adsorb the common ions from the dispersion medium. As a result, a negatively charged sol is formed. But let's see other example. When we have a potassium iodide solution and we add it to silver nitrate solution. Now the dispersion medium is of silver nitrate. Again silver iodide will be formed and this will adsorb common ions from the dispersion medium. That is, silver ions will be adsorbed and this results in the formation of a positively charged sol. Let's see other example. If we have ferric chloride and it is added to hot water, then positively charged sol will be formed because this hydrated ferric oxide will adsorb ferric ions from the dispersion medium and this will lead to the formation of a positively charged sol. When this ferric chloride is added to sodium hydroxide solution, then hydrated ferric oxide will be formed and this will adsorb hydroxide ions from the dispersion medium and thus a negatively charged sol is formed. Now these sols have been formed. Now what they do, they start attracting counter ions from the dispersion medium. So this sol is formed. This is the colloidal particle. This has adsorbed the common ions. Now this start attracting the counter ions from the dispersion medium and thus a second layer is formed. The first layer which is formed by the iodide ion is called the fixed layer and the second layer is known as the diffused layer. Now these two layers comprise the Helmholtz electrical double layer. So the combination of two layers of opposite charges around the colloidal particle is called Helmholtz electrical double layer. Now whenever there is charge separation, it is a seat of potential. So the potential difference between the fixed layer and the diffuse layer of opposite charges is called the electrokinetic potential or zeta potential. So these are the important terms. Helmholtz electrical double layer, that is the combination of two layers of opposite charges which are formed around the colloidal particle. This is the colloidal particle, this is the fixed layer, this is the diffused layer, and whenever there is a charge separation, it is a seat of potential, and as a result the potential difference between the fixed layer and the diffused layer of opposite charges is called electrokinetic potential or zeta potential. So these are the important terms. Now if the precipitate do not have double layer, then what will happen? They will come close to each other and as a result they will coagulate. So the double layer repel them at large distances of separation and this repulsion prevents their close approach and thus the colloid is stabilized. When you add more electrolyte to sol, then what happens? There is reduction in the zeta potential and also the diffused double layer will be suppressed. This decrease in electrostatic repulsion between particles to a large extent and colloid precipitates. See what happens when you add more of the electrolyte, the opposite charges become neutral and as a result what happens? There is a decrease in repulsion and thus the colloid precipitate. So repulsion is very important because repulsion prevents the particles from making aggregates, and once the aggregates are formed, they are going to lose their colloidal dimension. So repulsions keep them apart and do not allow them to aggregate. So colloids are very sensitive to oppositely charged ions because again if these ions are present, they are going to neutralize the solution and thus as a result of attractions the colloid is going to lose its dimensions and thus its stability will be gone. Let's discuss about electrophoresis. This electrophoresis confirms the existence of charge on colloidal particles. when electric potential is applied across platinum electrodes which are dipped in a colloidal solution, then colloidal particles move towards their respective electrode. The positively charged particle moves towards the cathode and the negatively charged particle moves towards the anode. This movement of colloidal particle under an applied electric potential is called electrophoresis. If this electrophoresis is prevented by certain means, then it is found that the dispersion medium begins to move in an electric field, and this phenomena is termed as electroosmosis. Then we come to the next topic, coagulation or precipitation. We know that charge is required for the stability of the lyophobic soles. But if this charge is removed, then what happens? They form aggregates and then they settle under the force of gravity. This process of settling of colloidal particle is called coagulation or precipitation of the sole. The various methods to coagulate the lyophobic soles are: number 1, electrophoresis. In this, the colloidal particles, they move towards the oppositely charged electrodes. They get discharged there and hence precipitated by mixing two oppositely charged soles. For example, we have one positive sole, another negative sole, and if we take them in equal proportion, then what will happen? They will coagulate, and this type of coagulation is called mutual coagulation. They will neutralize their charges and thus they will be precipitated. Then the third is by boiling. When the sole is boiled, then what happens? Its adsorbed layer is disturbed. Why it is disturbed? Due to increased collision with the molecules of the dispersion medium. As a result of this, their charge is reduced and they ultimately settle down in the form of a precipitate. By persistent dialysis. Dialysis is a method of purifying the colloidal solution, but if it is carried for a long time, then traces of electrolyte which are present in the sole, they are also removed, and ultimately this colloid becomes unstable and ultimately it's coagulate. By addition of electrolyte. When excess of electrolyte is added to the colloidal particles, they are precipitated. Now why this happen is that they interact with ions carrying the charge opposite to that present on themselves. As a result of this, there is neutralization, and thus this neutralization lead to their coagulation. Now the ion which is responsible for neutralization of charge is called the coagulating ion or the flocculating ion. For example, we have this negative ion causes the precipitation of a positively charged sole. Let's first understand a rule, Hardy-Schulze rule. It states that greater the valence of the flocculating ion, greater is the power to cause precipitation. For example, if we have a negative sole, then the flocculating power will be in the order aluminium ion 3 positive, barium has 2 positive, and sodium has 1 positive. So this will be the order, that is, greater is the valency of the oppositely charged ion, greater is the power to cause precipitation. So aluminium ions will precipitate the negatively charged sole with a greater speed. So less concentration of this aluminium ions will also be required. For example, we have the positive sole and the flocculating power of the ions will be in the order F4 negative, 3 negative, 2 negative, means greater is the valence of the oppositely charged ion, greater is the power to cause precipitation. Now the minimum concentration of the electrolyte which is required to cause precipitation of a sole is called coagulating value. The minimum concentration has to be taken in millimoles per liter, and this has to be observed for 2 hours. So the minimum concentration of an electrolyte in millimoles per liter which is required to cause precipitation of a sole in 2 hours is called coagulating value. The smaller the quantity needed, the higher will be the coagulating power of an ion. For example, in this coagulation of a negatively charged sole with aluminium ions, the smaller quantity of aluminium ions is needed. In this coagulation of a positive sole with this FeCN6 4 negative ions, the small quantity of this is required. Thus, the smaller the quantity needed, this shows that higher will be the coagulating power of an ion. Now, the higher coagulating power of an ion means it has the greater valence. So, greater is the valence of the flocculating ion, greater is the power to cause precipitation. This is Hardy-Schulze rule. Let's discuss about the coagulation of lyophilic sols. The two factors which are responsible for the stability of lyophilic sols are charge and solvation. If we remove these two factors, the lyophilic sols can be coagulated. Now, how these factors can be removed? Charge can be removed by adding an electrolyte, and solvation can be removed by adding a suitable solvent. For example, if alcohol or acetone is added to hydrophilic sol, then what happens? There is a dehydration of the dispersed phase, and under this condition even a small amount of electrolyte can bring about coagulation. So lyophilic sols can be coagulated by removing their charge or by removing their solvation. The solvation is removed by dehydrating the dispersed phase by adding solvents such as alcohol and acetone. Now, protection of colloids. The lyophilic sols, they are more stable than the lyophobic sols because they are extensively solvated, that is, they are covered by a sheath of liquid in which they are dispersed. So lyophilic colloids have a property of protecting the lyophobic colloids, so they are also known as protective colloids. When a lyophilic sol is added to lyophobic sol, the lyophilic particles, they form a layer around the lyophobic particles and thus protect the latter from electrolytes. For example, this is a lyophobic sol and you have added a lyophilic sol, then what will happen? So this lyophobic sol is protected from this protected by this lyophilic sol from the electrolytes. So that is why the lyophilic colloids are also known as protective colloids.